In this video we will discuss two general properties of systems. These properties, linearity and time invariance, lead to simplifications of mathematical analysis and greater insight and understanding of system behavior. Linear time invariance is abbreviated as LTI. To facilitate the discussion, it's useful to recall the block diagram representation of a general discrete time system as shown in the figure. When applying a signal xn to such a general system, this will result in an output yn. This input-output relation will be denoted by the arrow symbol as shown in the slide. When delaying the signal xn by n0 samples, this results in a delayed signal xn minus n0. By using this delayed signal as the input of the same system, the output is denoted by wn. On the other hand, by delaying signal yn by n0 samples, the result is yn minus n0. A system is time invariant, abbreviated as TI, if and only if the output wn is equal to the output yn minus n0. In other words, when input xn produces yn, a system is time invariant when a delayed input results in an output which is delayed over the same amount of samples as the input. It can be shown that an FIR filter is time invariant as follows. From the difference equation, it follows that the delayed output signal writes as the given equation. On the other hand, when using in the upper branch the signal Vn for the delayed input signal xn minus n0, and using the difference equation which describes the FIR filter, this results into the given equation, which is equal to the equation above, the delayed output. Linearity of a system can be shown as follows. Assume when applying signals x1n and x2n to the same system, they result into the output signals y1n and y2n respectively. Combining and weighting these two output signals as alpha y1n plus beta y2n results in the output signal wn. On the other hand, when first combining and weighting the two input signals to a new input signal as xn is alpha x1n plus beta x2n, and then applying this new input signal to the same system, this results into an output signal yn. A system is linear if and only if the two output signals yn and wn are exactly the same. It can be shown that an FIR filter is linear by the following steps. Use the difference equation for the system at the left-hand side of the figure. Substitute the weighted combination of separate input signals. Split the summation, and it follows that the output yn is the same as the output wn of the right-hand side figure. In the following example, we will show how the LTI property can be used to find the impulse response of such a system when responses to different input signals are known. Assume the impulse response of the LTI system to the input sequence x1n is y1n, and the response to input sequence x2n is y2n, as given in the equations. The question is to find the impulse response hn of this LTI system. From the linearity property of the system, it follows that linear manipulations to input signals lead to the same linear manipulations of the output signal. This implies that the addition of x1n plus x2n divided by 2 results in y1n plus y2n divided by 2. When adding x1n plus x2n and divide by 2, we obtain delta n. On the other hand, when adding y1n plus y2n and divide by 2, we obtain, for the output, delta n minus 1. The impulse response of a system is defined as the response of a system to a delta pulse, delta n. By linear manipulations of the input signal, we created a delta pulse. Thus, the impulse response of this LTI system is equal to delta n minus 1. Now we will show that the convolution sum procedure holds for any LTI system. For this, we start by writing a sequence of input samples as a, possible infinite, sequence of delta pulses. For any LTI system, we can perform the following steps. When applying a delta pulse to the input of the system, the result is the impulse response Hn. Because of the time invariance property, a shifted delta pulse over L samples will result in a shifted impulse response Hn minus L. Multiplying the shifted delta pulse with a constant xl will result in xl multiplied by Hn minus L because of linearity. Finally, when summing over all indices L will result into the given output signal y of n. Concluding, it follows that indeed the output y of any LTI system can be evaluated by the convolution sum procedure of the input x with the impulse response h of the LTI system. Usually, the mathematical convolution sum procedure is described by an operator, which is symbolically denoted by a star. As an example, we can describe the convolution sum of a signal xn with a delayed delta pulse over n0 samples with the convolution operator as depicted in the given equation. Writing out this expression in a mathematical way results into the given infinite summation. However, because of the delta pulse in this summation, all indices L result into 0, except for the index L is n minus n0, which leads to the result xn minus n0, which is the input signal xn delayed over n0 samples. Furthermore, it can be shown that the convolution operator is commutative. This implies that the convolution of xn with hn is the same as, the other way around, the convolution of hn with xn. Mathematically, the proof is given in the following steps. Because of the fact that an FIR filter is LTI, it follows that the commutative property also applies for this filter. In other words, there are two different ways to evaluate the convolution sum of an FIR filter. The first way is as follows. The difference equation describes the output yn as a sum of m weighted delayed input signal samples. The impulse response of the FIR filter is given by the m weights of the FIR filter. So we can replace the weights bk in the difference equation by the impulse response values hk. This expression represents the convolution sum, which can be described by the convolution operator of the impulse response hn with the input signal samples xn. Because of the commutative property of an LTI system, we can turn around x and h, which leads to an alternative second way to describe the convolution sum of an FIR filter. In this approach, the given summation involves the product of x with index k and the impulse response h with index n minus k. Because of the fact that the index of the impulse response is limited in the FIR case, the question is, what are the values of the index boundaries on the convolution sum in this case? We have seen that in the general case these boundaries are in between plus and minus infinity. For an FIR filter, however, the index of the impulse response is limited in between 0 and n minus 1. This implies that within the summation the index n minus k of the impulse response has to be within this range. On the one hand, this implies that the index n minus k has to be larger than 0, or k must be smaller than n. While on the other hand, index n minus k has to be smaller than m minus 1, or k has to be larger than n minus m minus 1, which results in the equation as given on the slide. Concluding, it follows that we can describe the convolution sum of an FIR filter in two different ways, namely in the first approach as a convolution of the impulse response h with the input signal x. In this approach, the boundaries of the summation are in between 0 and m minus 1. In the second approach, as a convolution of the input x with the impulse response h. For this case, the boundaries are in between n minus m minus 1 and n. We can show the commutative property for the convolution sum procedure of an FIR filter by comparing the following two animations. In the first animation, we see the convolution result of an input signal xn with the impulse response hn. In this case, we mirror the impulse response hn and then apply the other steps of the convolution sum procedure. In the second animation, we switch the order of the convolution sum procedure. Thus, we convolve h with x. So now the first step is not to mirror h, but x, and then apply the other steps of the convolution sum procedure. The result of this procedure is the same sequence of delta pulses as in the previous case. So indeed, the commutative property holds for this example. An LTI system has also the associative property. This implies that the result of the convolution of x1 with x2 convolved with x3 is the same as the convolution of x1 with the result of the convolution of x2 with x3. The proof of this associative property is given in the following steps. The associative property of an LTI system results into the following so-called Cascade equivalence. This implies that there are different representations of a cascade of LTI systems. This can be shown as follows. Assume we are given the cascade of two LTI systems with impulse responses h1n and h2n respectively. In the first representation, the output yn is obtained by first convolving x with h1 and after that convolving the result with h2. Because of the associative property of both systems, we can obtain the same output yn by convolving X with a convolution result of H1 with H2. In other words, for the second representation, we can combine the cascade of two impulse responses H1 and H2 into one new combined impulse response H, which equals the convolution sum of H1 with H2. Furthermore, because of the commutative property, we can switch in this last representation the order of H1 and H2, while splitting this new combined system results in the third representation, in which we obtain a cascade of two LTI systems, but now the order of H1 and H2 is switched. Concluding, it follows that for any cascade of two different LTI systems with impulse responses H1 and H2, there are three alternative ways of representation. First, the cascade of system H1 and then H2. Or second, switch the order of H1 and H2. Or third, combine system H1 and H2 to one new system with impulse response H, which is equal to the convolution sum of H1 with H2. In this example, we have a cascade of LTI system 1 with impulse response H1 and system 2 with impulse response H2. The realization scheme of the cascading of these two systems is depicted in the slide. We can combine these two cascaded systems into one new system with impulse response Hn, which can be evaluated as the convolution sum of H1n with H2n, which results, in this example, in the given expression. From this expression we obtain an alternative realization of the cascade of two systems, as depicted in the slide. Finally, we note that the cascading of two FIR filters results into an FIR filter again. The finite length of this combined filter equals the sum of the length of both individual filters minus 1. This ends this video in which we explained the concept of linear time invariance. Thank you for your attention.